Welcome to the course on power quality. Today we would like to cover this AC-DC converters that cause the power quality problem. We normally use like the outline of the presentation will be today introduction, then state of the art, classification of conventional AC-DC converter and single phase conventional AC-DC converter, analysis of single phase conventional AC-DC converter and 3 phase AC-DC converters, analysis of 3 phase conventional AC-DC converter with the numerical examples, summary and then the references like. So, well, the objective of the lecture is that we like to discuss what is the requirement and applications and then configuration of AC-DC converter, control of AC-DC converters and then analysis and design of AC-DC converter, then method of modeling and control of AC-DC converter. So, coming to like a large number of the load use AC-DC converter as a front end converter ranging from few watts to megawatt rating, and such converters can be classified based on various basis such as nature of AC supply, control of semiconductor devices and the circuit configuration. So, depending upon the type of filter used for filtering the rectified DC, their behavior vary in the number of ways on AC mains, and such converter exhibit poor power factor at AC mains generally used due to the harmonics only or but with the reactive power. So, well, the key performance parameters of these AC-DC converter or rectifiers, we call it like voltage relationship, then current relationship, rectification ratio, then form factor, ripple factor. Of course, on the grid side, we have a distortion factor, displacement power factor, true power factor, and of course, if it is a transformer is utilized at the input, we call it transformer utilization factor like. So, coming to state art on this typically of AC-DC converter. So, now the new solid state self commuting devices such as MOSFET, IGBT and gate run of thyristors are used, and with that of course, we have to use improved control approaches also with varying configuration, and of course, we use the normally the DSP or the microcontroller which have come from the revolution of microelectronics. Of course, we have to use the sensing devices like for Hall effect current sensor, voltage sensors which are manufactured by many make like ABB, LM, HEME, and of course, we use the high speed and high accuracy microcontroller and digital signal processor for implementing the control of these converters like. So, well, application of these AC-DC converters, I mean we have in many applications and where they cause the power quality problems, I mean if we have not properly designing like. So, the typical example may be like a switch mode power supply, the mobile chargers, then electric vehicle chargers which are coming up very much now because of the electric vehicle. Almost even a government of India have decided by 2030 we must have all vehicle to be electric vehicle. So, the electric vehicle charger, I mean supposed to be chargers have to be in a big way. So, they also use virtually because battery is the DC by DC charging and supply normally we have a either single phase or 3 phase depending upon the power. So, all the different kind of vehicle chargers are now coming up, or you have a LED driver circuit for the lighting purpose, maybe in different power level starting from few watts it goes to like a maybe a even 12 to 18 watt typical example, and or computer power supplies or the motor drive. I mean most of the your AC motors which are brushless motors like whether it is a squirrel cage induction motor or it is your permanent brushless motors or you have a reluctance motor or synchroreluctance motor, they are using now the solid state variable frequency drive, and they also use this at the front end the AC-DC converter and then followed by the inverter driving the motors. So, I mean what mean that these AC-DC converter are extensively used like, or maybe in home inverters because you have to charge the battery from the first from the your supply. So, that use AC-DC converter or welding machines, high frequency welding machine where we use the AC-DC converter first for rectification, then we convert into high frequency so that transformer size is reduced, or even typically like even a 2-day ceiling fan using permanent brushless DC motor. So, we convert AC into DC and then DC into 3 phase AC for driving the 3 phase permanent brushless DC motor fans, or maybe people start using like a your switch reluctance motor. So, there also we first convert AC into DC and then we use of course, the different kind of convert depending upon the type of motors like. So, these are some of the applications and some more applications where these all equipments are used like a steel rolling mill, like a variable frequency drive, paper mills, printing presses, textile mill, traction system, home appliances, portable hand tools and of course, HVDC where we use AC to DC conversion and then further DC to AC conversion, and many more such examples. So, there are plenty of examples of AC DC converter, I mean which we use it like. And if we talk about this classification of conventional AC DC converters, as most of these create the power quality problem at the grid, because most of the application interface are through this AC DC converter, which causes power quality. So, we can classify it into two broad category like single phase and three phase converters, and single phase further we can of course classify it like uncontrolled and semi controlled, and uncontrolled we can classify further like half wave, full wave, bridge and voltage doubler. Voltage doubler itself half wave we will discuss with the circuit, it has a I mean lot of applications, I mean like typically in the appliance industry, and then semi controlled half wave, full wave and bridge, and fully controlled of course we have a half wave, full wave, bridge, and then we have a dual converter. Dual converter can be for half wave, full wave or bridge in fully controlled converter. So, similar classification we have of course this conventional AC DC converter for uncontrolled, typically again half wave, full wave, bridge, and here of course we have a multipulse also. I mean and multipulse can be again isolated, non-isolated, because you might be using transformer or you may not be using transformer. And when we have a semi control, so you have a half wave, full wave, bridge, but fully controlled converter you have a further classification half wave, full wave, bridge and dual converter, and then dual converter can be half wave, full wave and bridge, and then you have a multipulse which can be non-isolated or isolated. So, you have this glossary of conventional AC DC converters, I mean which are used in majority of applications, and you can call it like if we talk about uncontrolled, the word which you are looking, they have a very extreme kind of a harmonics injection into the supply system, or they draw the harmonic current from the supply. Of course, if we talk about semi control and fully control, they not only draw the harmonics, but they draw the reactive power also. So, because of this the power quality at the AC side, I mean on the grid, is deteriorated in most of these converters like. So, first we like to these, and then we like to look into the improvement in these AC DC converters, so that power quality inherently improved in these converters like. So, coming to first like a single phase conventional AC DC converter, I mean first category is your half wave. Half wave start with the simple, we use in very low power rating like probably few watt only, I mean like either first as a simple load, then maybe inductive filter, then capacitive filter to drive a voltage source, or LC filter. So, these are the typical kind of configuration are used in different applications depending upon the power rating in a half wave. Half wave is also very extensively not only used connected with the grid, but it also used typically in the final stage of the switch mode power converters. We will discuss that also there, I mean like. And these are the typical full wave, I mean with the push pull configuration, I mean with the simple load, or you have a inductive filter, or you have a capacitive filter, or you have LC filter. I mean you can just see it, I mean if all these will certainly have a power quality problem, harmonics typically, I mean you draw the harmonic current from the supply, in spite you have to use the transformer here because of the you are using this push pull configuration. But if you really put like typically a highly inductive load, then you get a square wave current from the supply. But if you put a capacitive, then you get a peaky current. Here crest factor is 1, here crest factor goes to 2 to 3 typically in that case. But you put a small inductor, then certainly the crest factor reduces and you go to the shape in between the two case like, I mean also. So, they are also extensively used when you want to reduce the voltage low level, I mean, and then with these filters like. Then we have a full bridge, I mean simple full bridge, or you can have it with the inductive filter. If you have a highly inductive filter, you have a square wave current on the supply side that inject the harmonics. But of course, in diode rectifier we do not have reactive power burden much, but if you put a capacitive, then you have a peaky current and draw very large amount of harmonic. Here harmonics are not so high, maybe like a maximum it can go 48% THD, but here the THD goes as high as maybe in some applications like switch mode power supply, it goes as high as maybe 80 to 90%. Third harmonics is quite dominated, which also causes excessive neutral current, which we discussed in previous cases like. And if you put a like a inductor here, then case comes in between the two, that you may not have a very peaky current, but of course, you get a good quality DC because of LC filter, but you also have still the harmonics on the supply current also. So, you will be having somewhere in between like a 48 to like a 90% kind of the THD on the input supply current. Then this is the special circuit which we call it voltage doubler. This have a very special purpose of converter, that you have a lot of appliances that typically I can talk about, like you want to have appliances like hair dryer, or you might have a typically your electric saver. I mean these are the travelers are using in North America. So, if you put the switch down in all these circuit, and you can operate the appliance at 115 volt. So, if you are going in North America, their supply system is around 110 to 120 volt. So, you can operate on lower the switch, and when you are in a Europe or India or this Asian part of continent, normally single phase supply 230. So, you can put the switch upper and you can have operating this converter with the 230 volt, but output voltage will remain almost the same in that case. So, your load will not be affected. So, in all these appliances which you might be operating, and this is a one of the very simplest and lightweight low cost solution compared to otherwise you might be using the transformer, which power transformer, which is a bulky, costly and even noisy, so as well as lossy. So, here you are simply using the diode rectifier, but the problem is here of course, you will be drawing large amount of harmonics from the supply system, because it's a capacitive filter is used at the out. So, you will get a peaky current like also in the supply. Well, that is typically uncontrolled. Now, we are coming to semi control. So, you have a half wave semi control, because you have one thyristor, one diode. So, when the thyristor conduct, you have energy. After that, if you have a of course, load inductive, so you have a Fourier reaction. Here of course, you are putting to provide inductive, and then or you have a capacitive here, or you have a LC filter. So, this is what we call it semi controlled half wave converter, and this is full wave semi controlled converter. Free wheeling is provided by this in like in different circuit, depends on, and then you have a bridge configuration with the different kind of filters. If you can look into the bridge semi control converter of different configuration, maybe you have a 2 thyristor 2 diodes, and some cases you have only 4 thyristor with 1 diode, or first case 2 diode 2 thyristor with different kind of filter arrangement. So, this is like a kind of you can call it like a semi converter control. And then we have fully control with the half wave fully control converter with the let us say different kind of filter. You have with no filter, then inductive, capacitive and LC filter like, and then you have typically fully controlled full wave converters with no filter, then inductive, capacitive and your inductive capacitive filter like also. Then we have a bridge like with no filter, inductive filter or capacitive filter or LC filter, this fully controlled converter. So, these are the extreme configuration. We are talking about all possible configuration where you can think about, but it certainly depends on the performance of it, with varies with the filter like or you have a dual converter in single phase with the half wave, full wave and bridge configuration like a dual converter. If you want output voltage to vary output voltage, typically you might be running your DC motor, small DC motor. So, you want to change the direction of rotation, you want to have regeneration also, that is possible to change the voltage and current direction by this dual converter like. So, of course, in case of the single phase, the filters are commonly applied in rectifier circuit for smoothing out the DC output voltage of the load, but this affects certainly the power quality on the input side. So, they are classified like input inductor input filter, capacitive filter, or your inductor input filter preferred in high power, and where the capacitive input filter suitable for low power application. So, you are using different kind of filter which we have shown in the circuit like but performance changes with the filters. If you are using inductive filter at the input supply, you will have a typically the current will be flat, crest factor will be less than sine wave, but if you are using LC filter it is in between, but if you are using only capacitive filter, crest factor goes very you draw the peaky current like. Also taking a simple case, if you are using a full wave with the let us say inductive filter, you will get a kind of ideally very high infinite inductor, you will get a kind of your square wave current and the kind of voltage you will get. But if you certainly if inductor is not so high, you will get the certainly some ripple here in the load current, but it has a quite substantial total harmonic distortion drawn from the supply current. And if you have a capacitive filter, you will certainly draw peaky current. When think about, you will be drawing the current only for the period when your supply voltage is more than the capacitor voltage. So, this is the only portion. So, you are doing in positive half cycle this kind of current and negative half cycle this kind of current. So, you will be drawing a current for very short period, peaky current. So, crest factor will be very high, as well as the harmonics also will be very high. In some of the application, of course, this may not be exactly the case, it depends on duration, the time constant of this circuit, filter and equivalent load resistance. So, this period may go on changing, it might be like might be out of 180 degree, it might be 60 degree or 90 degree or 120 degree, but certainly it will not be, it depends on the DC level, voltage level and value of capacitors like. The value of capacitor go on increasing, the duration go on reducing, but ripple will be less in the output voltage, but capacitor is less, duration will be more, but ripple in the output voltage will increase. So, it depends how you really, but the crest factor of this current is quite substantially high, and this kind of the kind of situation we have in many applications like we will talk about that later. Like coming to the how typically half wave. I mean half wave you will get only the current in positive half cycle, where the voltage is in positive high, and you can see the DC components also you are injecting into the supply system. And because of this reason, of course, it used for small battery charging, very low power battery charging, but you can say you are not only injecting the harmonics, but you are injecting virtually even the DC component also into supply system, which may saturate even your transformer of the supply system also. So, coming to with an example of your a DC motor have a series armature resistance of 10 ohm fed with the half wave rectifier from a single phase 230 volt 50 hertz AC means. Calculate the load average voltage, supply RMS current, active power drawn, power factor, reactive power, crush factor, distortion factor, TAD at the full speed. The motor back EMF is 100 volt. So, in single phase half wave with the RL load, you can find out the conduction period, you can find out, I mean it will conduct when your, I mean start conducting when supply voltage goes greater than your back, typically the back EMF. So, that is the duration. So, that is at this angle is to start the current, and it will quench according to inductor little more. So, from this you can find out the average current typically correspond to this angle or so. So, that is come average current, and then you can find out the RMS current corresponding to that with the data. So, RMS current comes this, then the active power consumed by that is virtually going to DC motor, this is the armature loss. So, that is the power consumed 1626.5 watt, and operating power factor now you can calculate the power, active power divided by VS RMS, IRMS we calculate, so it comes 0.65, and reactive power drawn from this we can calculate. So, there is a substantial reactive power also drawn for this circuit like. And then you can have a crush factor, I mean that crush factor, because you are drawing peaky current quite substantial. So, crush factor is peak upon RMS. So, you will get 2.21 in place of root 2 in sine wave of which is 1.41, and distortion factor, that is fundamental current divided by the total RMS current. So, that also come by 0.69. Ideally, it should be 1 when there is no harmonics like, and the total harmonic distortion you put the value, it comes 100.04%. I mean ideally it should be like a almost 0 in sine wave. So, coming to half wave control, I mean these are the typical waveform. So, you can see how the current will be drawn from the supply of this shape. Ideally, we should take sine wave, but you are drawing only the DC component also into that, not only AC component from it, and that is the kind of current you are drawing typically from diode, means that is a supply current, and what will the voltage across the capacitor across the load like. And then you can do the calculation of this your output average voltage, RMS voltage. So, such load certainly will cause typically a reasonable power quality problem. So, coming to like a of uncontrolled full wave, the full wave can be bridge or it can be full wave of this midpoint also. Normally bridge preferred, because this normally in bridge you can avoid the transformer, provided you are matching the voltage, then you can use this configuration which will have certainly less losses, because here 2 diode drop are there, it is single diode drop is there. But if you have a highly inductive load, then certainly you will get supply from kind of this kind of a square wave current typically, I mean like where the output current is of this nature, and this you can clearly see that this has a substantial harmonics, like ideally it might have a TAD of 48% with third harmonic, one third of the fundamental and fifth 1/5 or so. So, coming with an example of this, like you have a single phase rectifier with the highly inductive load, and you will have supply voltage. So, supply current, I mean for all these data you will find of this nature, there is the output voltage and output current, and you can calculate all these. Typically the data is given that your supply RMS current will be as the load current, and fundamental current will be of 2 root 2 upon pi, that is 4 upon pi, that is the peak divided by root 2, that so it becomes 2 root 2 pi upon pi into I 0. So, it becomes 10.804 ampere, and the crush factor is the typically peak upon RMS. So, peak is here same as 12 and RMS is also 12. So, it is a 1, and distortion factor is IS1 upon this. So, it comes 0.9, and displacement factor, because a diode. So, you will have a fundamental current in phase with the fundamental voltage. So, it is 1, and power factor is 0.9. This reduction in power factor from unity to 0.9 only because of the harmonics, not because of the reactive power. And the total harmonic distortion, if you put the value, it comes 48.43% like. So, harmonics are causing typically reduction in power factor, or it will increase the current RMS current in the supply system compared to the power which you are drawing here. And the typical example, if you have a that was highly inductive load, if you have a capacitive filter, I mean like here in the load, you will draw just the current only, peaky current only in the positive half cycle and negative high cycle of this manner. I mean like this kind of peaky current, I mean the current will be drawn only when your supply voltage goes more than the capacitor voltage. I mean that is the virtually the load voltage also. And the typical example corresponding to this is single phase diode rectifier have a displacement factor 0.97 and TID of 60%, it is doing 2000 watt at 220 volt 50 hertz AC source and correct factor is 3 of AC current. Calculate the power factor, RMS current and peak current of the AC mains. So, after making the model of and putting this data, the waveform like if supply voltage is this, but you can see the current of this. This will have a quite large harmonic like a 60% TID and displacement factor is also there, and this is the output voltage and this is the current drawn. So, current is down only the portion where your capacitor is getting charged, and that portion is quite small as you can see the current here. So, based on this, I mean we can have a quantitative calculation. So, supply voltage is Vs 230 volt, frequency 50 hertz and TID is given of supply current 60% and active power drawn is 2000 watt and displacement factor is your 0.97 and correct factor is 3. So, what is asked here, the distortion factor, that is 1 upon 1 plus TID square. So, it is a 0.857 and power factor is displacement factor multiplied distortion factor, and putting the value which is calculated and given here, it power factor is 0.832. So, this is because of reactive power and this is because of the harmonics. So, finally, power factor reduces to this, and now we can find out supply current, that is power, RMS voltage and power factor. So, that is the supply current 10.45 ampere and the peak current, that is correct factor into RMS current. So, this comes 31.363 ampere. So, you can just see that this much large current, I mean usually for 2 kilowatt from single phase supply we must not draw typically more than typically 10 ampere, but it is drawing around 31 ampere peak like I mean. So, that is because of the, you can call it the peaky current drawn from the supply like I mean. So, coming to full wave uncontrolled with the center tip midpoint, I mean like connection. So, these are the calculation for of course for output, and of course, these are the typically I mean the output or the different rating for different kind of these conventional rectifier, the different you can call it ripple factor, transformer and all utilization factor like on. So, coming to now 3 phase conventional AC DC converter, I mean they also have a lot of power quality problem, like you can say half wave with no filter, with inductive filter, with capacitive filter and with this. So, they also draw the let us say the even a not only AC component, but they draw DC component. So, that is the reason they are not used I mean in high power, but these are the full wave. So, we use the transformer which convert 3 phase into 6 phase, and now with the 6 phase in full wave we have to use the 6 diode rectifier, 6 diodes, and which give the 6 pulses in input. But of course, in supply we will get like a kind of Cauchy square wave which we discuss in 3 phase converters, and of course, with the inductive filter, capacitive filter and LC filter. And this is the bridge like I mean normally we use the bridge with the simple load or with the highly inductive load or a capacitive filter we put it. All the variable frequency type you will find this kind of capacitive filter. I mean we have a we were showing the variable frequency type. So, we have this. So, it will draw very peaky current, and the TID of the current is normally around 60%, 60 to 65%. But if you put a inductive with this, the TID can be reduced to around 30 to 30, but this is still quite high like a 30 because standard allows hardly 5% total harmonic distortion. So, all these I mean you can call it like a this conventional converter, I mean they draw very high harmonic currents like, and so and this is kind of 12 pulse with simple with no filter, with inductive filter, capacitive filter, and with as you increase the number of pulses, certainly if it is a 12, so below 11th harmonics are eliminated automatically because of the design and construction of it, but still higher order harmonics also will be there substantially in that case. So, you will still have around 15 to 20% TID in the supply current, which is not permitted, like you allow only less than 5% or so. And these are isolated configuration of this 12 pulse configuration. You can connect them output as in series and parallel because they are isolated. And typically in some application we connect them parallel to if we have a high voltage, if we need high current, so we connect them parallel. So, that also give it like a TID order of typically around 15 or 15 to 16% or so. I mean because of inductance provide some kind of filtering even with the capacitive kind of load like. And then this is semi control with of course half wave semi control, but it also draws the DC component, but you have a control of voltage from 0 to for the output, but it have a very poor power quality because of the control. You have a pharyngeal control, means that provided that takes the reactive power from supply, as well as you have a harmonics, as well as not only harmonics, but you have even a DC component also from supply system. And this is the like a your full wave semi control because this diode at the output will certainly cause a failing action. So, it will not allow output voltage to go negative in any of the circuit, and of course, this is the output voltage can be varied from 0 to V, but you will still have a, depending upon the type of filter you are using, you will have a good harmonics as well as reactive power burden on the supply system. And with a full semi control bridge converter, so here also you will not get output voltage negative, but you will have a reactive power and harmonics in the input supply for all these converters. Like, so this is a typically fully controlled converter. I mean, here reactive power burden as well as harmonics you will draw in all these circuits, but of course, the waveform may change with the filter like LC filter or inductive filter. Normally, this circuit is normally used with the inductive filter, or load itself have a large inductance, but they have a harmonics as well as reactive power burden from supply system. It even draw the DC component, and it is again full wave bridge converter. You get the of course Cauchy square current, but you can understand you get the harmonics as well as reactive power burden on supply system in all these with. And this is bridge converter. So, here also you draw harmonics, and of course, with the fire angle you draw the change with the reactive power also. So, they are considered quite worst for as far as power quality is concerned. And this is dual converter. I mean, you can call it half wave dual converter, full wave dual converter, and bridge dual converter. I mean, so they also draw harmonics and reactive power from the supply, but of course, load it can give a 4 quadrant operation like a DC motor drive, or you are using for some other applications like, or like a 12 pulse you are using. So, harmonics get reduced because below 11th harmonics are not there, but still 11, 13 higher order are there, and apart from it draws the reactive power. So, control of output voltage in at the cost of reactive power drawn from the supply system. And this is of course isolated topology of this 12 pulse converter also. So, coming to like analysis part of this 3-phase uncontrolled AC/DC converter, and you can just see if we take a like a this isolated half wave, you will certainly draw the only DC component here. So, it not only drawing the harmonics, but even the second harmonics is substantial in this case. And if it is a bridge and you are putting a capacitive filter, you will be drawing hardly 2 notches, even discontinuous notch may be also there, a capacitive filter is there. I mean, we will discuss many problems such nature. So, it draws quite large amount of harmonics, even the TAD may be like a 60 to 65% or all of that, depends on the load nature also. And then this is a typical example. If you have a highly inductive load, then you will be drawing typically this kind of supply current Cauchy square wave. So, it has a harmonic, of course, not the reactive power burden because it is uncontrolled one. So, you have around 31% TAD in that case like also, and these are the typical calculation that you get 31% TAD in this case like also. And you have a even a because of the harmonics only you have a poor power factor, not unity, it goes to like 0.955 or so. So, taking a typical example like with the highly inductive load with diode rectifier, I mean after making a model with these data, you have a, if you have a voltage, but these are the supply current which are Cauchy square wave, output voltage and current. So, these have a substantial amount of harmonics like. So, we can of course, can have a calculation of all these are RMS current, and this is fundamental current we calculate. Then of course, active power we calculate output voltage, then the of course, the equivalent resistance, then we have a load power, then load supply RMS current, then distortion factor because of harmonics, then displacement factor, and then power factor. The power factor is poor because of harmonics, and TAD of supply current is 31.08% like. And this is 12 pulse converter. So, you have a supply current of course, in the supply here because of 12 pulse you will be you will not get less than 11th harmonics, but you will have a more closer to sine wave, but still you have around 15 to 16% total harmonic distortion of this current like. So, coming to now numerical examples on numerical problems on these conventional converters, the biphase half wave 2 pulse diode converter with midpoint is supplied 110 volt, and consider the 1 volt drop and load resistance of typically 10 ohm with the highly inductive load. Calculate the average DC voltage, diode peak current, and the power quality parameters like thrust factor, distortion factor, displacement factor, and power factor, and value of load resistance. So, coming to with this data, we have given supply voltage 110, and we can calculate the peak, then diode drop, then we can find out typically the output resistance, load resistance, and the voltage, output voltage, and then we get the peak voltage and peak current. Then we can have a average output power, and then we can have a typically peak current from this relation, and the RMS value of current, and then crest factor. So, it comes typically of your root 2 sine wave, then distortion factor because of the harmonics, I mean it comes 0.8, and displacement because it's a diode is 1. So, power factor goes same as the distortion factor. So, this power factor reduction is because of harmonics only. So, coming to another example, a biphase half wave 2 pulse converter, midpoint converter is supplied from 230 volt and resistive load 100, and calculate all these parameters of this circuit. So, we have a supply voltage given here, and we can calculate peak voltage, resistance in. So, we can find out average output voltage, then the average load current, then the power drawn by this line, and the AC power. So, we can have efficiency calculation, so that what is the efficiency of the rectifier, then ripple factor, quite distorted output also, then the peak current, RMS current in supply, and then the crest factor, and we got a RMS current and the transformer utilization factor, and then the comes to around 57%. Then you can call it fundamental current, which is, and distortion factor 0.81, and then your power factor, that is distortion multiplied displacement factor. So, coming to third example, biphase, a diode bridge rectifier with the 2-phase DC current, and with this data also, I mean, you can have a calculation, and it comes the crest factor 1 because of the square wave current, and the power distortion factor is 0.9, displacement factor is a power factor is 0.9, and TAD is 48% with of course voltage. Now, coming to this bridge configuration, I mean, the data given here in this case. So, you can find out like typically the crest factor is 1 because of square wave current, and distortion factor is 1, typically 0.9, power factor is 0.9, and the TAD of course because of square wave is 48.34. Coming to another example of this single phase bridge rectifier, which is given data here that 15 ampere current is here, and we can calculate the distortion factor and all the. So, after putting the data, we get the waveform supply voltage, supply current, output voltage, output current, and the calculation as far as this is like given the DC link current. So, we can find out RMS current is the same for square wave, and fundamental will be around that 0.9, then the output RMS voltage, then the typically distortion factor because of harmonics is 0.9, and displacement factor unit because they are uncontrolled, and then we have a power factor 0.9 and TAD around 48%. Of course, RMS mains current typically 15 ampere, of course, devices current and all those data are there, but you have a typically of your input power and the all data there like output voltage, distortion factor, displacement factor. So, a single phase uncontrolled bridge converter is supplied from 230 volt 50 hertz. Consider constant load current 30 ampere and diode voltage of 1. Compute the output voltage, distortion factor, displacement, power factor, total harmonic distortion, and diode and average current and reactive power. So, these are all computed data. So, here distortion factor comes 0.9, displacement factor 0.9, and power factor 0.9, and TAD 48%, and these are of course other data calculated here like. So, coming to a single phase fully controlled bridge converter is used to charge a battery of 1 kilowatt 96 volt from single phase AC mains. A large inductor is included with the battery with the 2 ohm resistance, and calculate the DC link current, AC mains RMS current, TAD, distortion factor, displacement factor, power factor, and RMS current. So, these are typical because thyristor will conduct only when typically this is more than you can call it the supply voltage more than your battery voltage. So, this is the type of current you are drawing. So, with the taking all data, so DC side current, then AC side RMS current from that, and we can have a total harmonic distortion factor, then your distortion factor, displacement factor comes in 1 because you are not able to control, and power factor is 1, and thyristor current is of this much ampere or so. 3-phase uncontrolled rectifier is used for battery charging of 20 kilowatt for 400 volt DC from AC 3-phase current 415. Large inductor is included. So, resistance is inserted to calculate the resistance, DC current, AC mains current, TAD, distortion factor, displacement, power factor, and RMS diode current. So, these are of course making a model. These are the typical current in supply, which have a quite harmonics. So, these are the calculation like we calculated. So, charging current of the battery we can calculate from here because we know power. Now, it is a DC link current is this much. Okay. Then we can calculate resistance from that to limit that current, and this is the from RMS current and total harmonic distortion and typically fundamental current. So, we got distortion factor. Of course, here we have a displacement factor unit. So, power factor is typically 0.5, and this is the of course diode current like. This is typical interesting example because this diode rectifier with capacitive filter is used with the variable frequency drive, and and after putting the value, these are the typical waveform of supply current, which is quite large in distortion. So, a 3-phase diorectifier consisting of 415 volt with large capacitive filter and DC supply the voltage source inverter fed induction motor type at DC link of 520 volt DC with the total circuit resistance of 2 ohm. Calculate the average DC current, RMS supply current, RMS fundamental current, input active power, TAD of the AC current, displacement factor, distortion factor, power factor and Cusp factor. So, coming to typically the solution part of 3-phase diorectifier with large capacitive filter, we have as a series resistance back EMF, and you can call it the AC supply current flows between 2 pulses of each half cycle from theta 1 to theta 2 and theta 3 to theta 4, which segments of AC line voltage are equal to greater than back EMF, that is your 520 volt, and at angle theta 1 the supply current increases and decreases to 0 at theta 2, reduces to equal. So, we can calculate the typically alpha 1 here, and we can calculate like this alpha, and from this we can calculate the beta, and we can calculate conduction angle. So, for this much period only out of 60 it is conducting, and we have another segment typically for the angle. So, there also we have a same conduction angle. So, 2 pulses of this much duration are there, and now we can calculate theta 1 at which it start, then its end first segment, second segment is start at this angle and ends at this angle. And once we know these angle, we can find out like output average current that comes equal to, for given data, it comes this value. Since the AC current with a couple of pulses in each half cycle, odd even symmetry, half symmetry, so RMS current, I mean from this relation we can calculate from this typically from the 1 node. So, it comes 22.88 ampere, and the fundamental RMS current from the power we can calculate, it comes 16.252527, and this is the peak current. So, we can find out typically given the average current here and the RMS current in the supply. Then say this is again fundamental current and power absorbed, then total harmonic distortion is as high as typically 99%, and displacement factor is unity here because diodes are used, and now power factor because of distortion is 0.7 because TAD is 100%, and the power factor is 0.71 and the Cusp factor is 1.46. The another example like typically fully controlled bridge converter supplying the supplied from 415 volt 50 hertz, the firing angle of thyristor is to be alpha equal to 60 degree. Consider the constant load current of 20 ampere with the thyristor voltage of 2 volt, compute the average output voltage, distortion factor, displacement factor, power factor, total harmonic distortion, AC means RMS current, thyristor average peak current, and the reactive power and peak. So, after making the model of these are the supply current drawn from this, which have a harmonics as well as reactive power burden, and this is the calculation with the all these data. So, we can calculate output average voltage, then we have a distortion factor, we have a displacement factor because firing angle is given at 0.5 and power factor is distortion multiplied so it comes for, and total harmonic distortion from the your RMS and fundamental current 31% and AC RMS current comes 16.33, and thyristor current we can find out conduct only for 120 degree, and then the input active power and then the reactive power and peak voltage. So, with this the conventional AC-DC converter are broadly classified based on single phase and 3-phase supply system. Further, various type of conventional AC-DC converter are demonstrated with relevant diagram. Analysis of most of the popularly known conventional AC-DC converter are given, and their impact on supply side quality are on power quality are analyzed, and these conventional AC-DC converter draw no non-sinusoidal current from AC mains, which consists of harmonics and reactive power component of current, fluctuating current and balance current. A number of practical examples of conventional AC are given with a view of proper exposure to the problem, and these are the references. Thank you.